Okay, so we've done continuity, x and y momentum. We're left with the energy equation. So let's look at that. It's a little bit different, right? Because now we're dealing with, instead of just velocities and densities, we're dealing with energy. So temperature, conductivity, things like that. Remember the energy equation that we came up with. It was this equation here, where we have this viscous dissipation term that can result in energy generation inside the control volume. So let's do the same order of magnitude analysis for the energy equation. So we're going to do order of magnitude for this entire thing. So let's look here at the first term. So the first term is going to be density times specific heat times U infinity. Now what is the dt dx? So dt, I guess, is going to be some delta t. So it's right over here maybe. So let's say delta t is equal to T s minus T infinity, right? It's the temperature difference between the surface and the free stream. That's the largest that we would have to deal with. So we'll just call that delta T divided by L. So that's the first one. The second one is going to be rho C V sub delta, delta T over delta, right, in our y direction. On the right-hand side, we have this conductivity term. So that is conductivity times delta T over L squared, because it's the second derivative. This term is conductivity times delta T over delta squared. And then the last term here is mu times U infinity squared over delta squared, because we're taking the first derivative and squaring it. Right? All order of magnitude stuff there. So what do we do with this? I guess the first thing is using the approximate model for V sub delta. We substitute that back in, right? That's down here in the lower left corner. So substitute that back in, and this becomes rho C U infinity delta T over L. So I guess we can conclude that this one and this one have the same order of magnitude. One thing that then I maybe want to do is I want to compare these two terms with the rest of them. So again, let's go through and divide all the terms by this guy and see what happens. So divide through, we would get, let's give myself some room here. So I'm going to come over here. I'm going to divide through on this term. It becomes K delta T over L squared times L over rho C U infinity delta T. And that becomes, there's an alpha in there, so it's alpha over L U infinity. And then let's also bring in the viscosity to this. So we're just going to manipulate it a little bit. We're going to multiply by viscosity over viscosity. So viscosity over viscosity. And that would give us something interesting, which is 1 over Reynolds number, Prandtl number. So the order of magnitude of that is 1 over Reynolds Prandtl, probably small. We can do something similar for this term here. I'll just tell you what the result is. So it becomes L squared over delta squared 1 over Reynolds Prandtl, which again is approximately 1. Right? Big number times a small number. And then the last term, so we can't throw this away because U infinity is probably large and delta is probably small, right? So a large number squared over a small number squared is still a very large number, or a large enough number. So of all of these, we would say the one I can get rid of is probably this one here. So we can then rewrite this as our simplified equation So that's our simplified energy equation. So I know this is this is tedious, right? But what we've done is we've gone through and we I guess have decided, based on all of this, that we don't need to think about the rate of change of the derivative of temperature in the x direction, right? So we can kind of get rid of that one. Sort of saying the conductivity in the x direction is unimportant. So we're only thinking about conduction in the y direction, which I guess intuitively makes sense, right? Okay.
Maybe I missed this.
Yeah.
From the previous slides, this internal generation term here, did we already prove all those other terms are unimportant?
Oh, yeah, I think I have that note here as well. Where did that go? Thank you. Over in the corner. G dot triple prime is approximately equal to mu times partial u with respect to y squared. So why is that? Let's see. So you can do the same. You can do the same type of analysis, and you end up with that. So what you need to say is that in most flows, this is going to be a small number, I guess. So you have to kind of look at the application for this for this derivative and see if it's small. For most flows, it's going to be small. Just think if they can add anything there. Yeah, so we're going to actually, I'll come back to, so this is as far as we can get at this point. I have a later slide, I think, that we'll come back to where we talk about like under which circumstances it is important or not. Thank you. Okay, so let's move on then to this slide, which is the summary of the simplifications we've made. So we have gone from all of this stuff on the left-hand side to what's over here on the right-hand side. Where's my temperature one? Oh, here it is. Okay. So we've gone to all of these sort of simplified cases. I guess the main conclusion is that we can get rid of y momentum entirely, and that we can make some simplifications to our viscous dissipation term. But otherwise, we just lost basically one term from each of the equations. All right, so then the remaining time today, what we're going to do is take this information. Again, you can't really take these equations, plug them in, and solve them analytically in most situations. I mean, you can kind of boil them down further, make some simplifications, but it's really hard to solve these coupled equations in real applications. So what we need to do is use these to help us develop correlations that we can then employ. And what correlation would be, you're trying to fit some data to the form of this equation that you would maybe derive from this. So let's look at how we would do that. And I guess the thing that you need to do for correlation is you don't want to go through the process of developing a correlation every single time you make a change in, say, the length of your pipe or the diameter of your duct or whatever it is, right? You always want to have this maybe general relationship that says, in terms of some normalized parameter, I can compute a quantity that I care about and then scale it back to my dimensional quantities that I do that are real engineering value. So what we're going to do now is go through these equations and figure out how to normalize them. Once we have them normalized or non-dimensionalized, we'll see something about non-dimensional parameters that come out of that process. And then we'll see how to apply that in correlations.